we saw that we could manipulate a step in a reaction such as flip the step or double the step, and that would have some change to we'd have something that we had to do to the change of enthalpy. So if we doubled a step, we'd double the change of enthalpy. If we flipped a step, we would flip the sign of the change of enthalpy. There's similar rules for KEQ. So what we're going to look at is what different manipulations are going to require us to do to the K. So let's see. If I have an equation written this way, I have 1 Kc, and when I flip this reaction, I want to see what happens to Kc. I want to see what I have to do to this value to get the new Kc. So my new Kc is going to be expressed by writing concentration of nitrogen times concentration of hydrogen cubed over concentration of the ammonia squared. So I look at the old Kc, and I see that to go from here to here, I actually flipped the Kc expression. I took the reciprocal of the Kc expression. So if I want to have this new value, I'll take what the old value was, but I'll take the reciprocal of it. 1 divided by 3.5 times 10 to the 8th. And that is equal to 2.8 times 10 to the negative 9th. Okay, so if I flip a reaction, then I take the reciprocal of the K to get the new value of the K. How about, let's see what happens if I multiply a step by something. So for example, here I'm going to multiply by 1/2. So if I multiply this whole thing by 2, by 1/2, by any value, let's see what we have to do. In this case, I multiplied nitrogen by 1/2, hydrogen by 1/2, ammonia by 1/2. The whole step is multiplied by 1/2. And let's see what the new K is. So it's going to be the products, concentration of ammonia, over the reactants, concentration of nitrogen to the 1/2, or square rooted, and hydrogen to the power of 3/2. Okay, so I can see to go from this expression to this one, what I did is I square rooted each thing, or I raised it to the power of 1/2. I took this, I multiplied by 1/2. This guy, raised to the power of 1/2. This guy, raised to the power of 1/2. So what I can see is, if I multiply a step by some value, I'm going to take the Kc and I'm going to raise it to the power of that same value. So I'm going to take 3.5 times 10 to the 8th, raise it to the power of 1/2, or square root it, and I end up getting 1.9 times 10 to the 4th. Okay, so anytime I multiply a step by some value, I raise the K to that same value, and I'll have the value of the new K. So if I had a system at equilibrium using these, and I wanted to use this K expression, I would just plug in the equilibrium concentrations, raise to these powers, and it would be equal to this. Same thing, if I took those same concentrations and plugged it in here, raised it to these values, I would get that value, that Kc. So I'm not changing the equilibrium conditions, but I have a new value to actually calculate the relationship in the equilibrium. So here's another. Let's imagine I have a Kc expression. I've got all these concentrations giving me a Kc value, and I want to know how the Kp relates. How are pressure and molarity related? Well, they are related because we know that PV equals nRT, the ideal gas law, and I can rearrange that just to see what pressure is equal to. Divide both sides by volume. Pressure is equal to the moles per liter, the molarity, these guys, times RT. What that means is if I took everything in this Kc expression and multiplied this by RT, and then it was squared, multiplied this concentration by RT and this concentration by RT and cubed it, I would get the pressures. I would get this new value, or the new expression with pressures instead, so I'd have the Kp equation. And since I had RT squared on this side and I had RT to the 4th, overall I would have 2 minus 4, I'd have RT raised to the negative 2. This gives me a new equation, which I don't need you to derive, but I do need you to be able to find it on your sheet, Greg, that you get to use for every test. And that is Kc is equal to, oops, sorry, it's Kp. Kp is equal to Kc times RT, gas constant and temperature in Kelvin, raised to the power of delta N. And if you don't remember what these mean, Greg even tells you that this is the gas constant, this is the temperature, and right below the equation it actually says where delta N equals moles of gaseous products minus moles of gaseous reactants. And that makes sense, because if I said 2 minus 4, I would have a negative 2, and that's what we said this would be, because we had to the power of 2 divided by to the power of 4. That gave us the negative 2. So let's calculate the Kp. Kp is equal to Kc, 3.5 times 10 to the 8th. You know what? Let's see. The gas constant is 0.08, 206. I'm not even going to use units because Kc doesn't use units, or at least AP Chemistry doesn't use units for these guys, so I'm going to leave them out. 298, whoops, 298. And that's all going to be raised to the power of negative 2. The way I have this written, it's a little confusing. No, it's not. The one mistake students make, or the couple mistakes, using the wrong gas constant. We're using the ideal gas law, so use the gas constant we used in the ideal gas law. Temperature has to be in Kelvin, 298. And make sure you take this and raise it to the power of your delta N before you multiply it by this guy. So order of operations. So when I plug that in, I end up getting 5.8 times 10 to the 5th. So really, plug that in, make sure you can get it, because that is one of the most common mistakes I see, is that students have a mistake with the order of operations. Next, for our last manipulation of K, what we can see is, so in Hess's law, we said the enthalpy of one step plus the enthalpy of the other step added up to be the total enthalpy. Let's see what it is for K. I will tell you, what you do is you take K of the first step, multiply it by K of the second step to get K overall. So the K for this guy is going to be K1 times K2. And now I shall prove it to you. Let's see what K equals for this guy. K is going to be the concentration of silver times the concentration of chloride all over that. 1, because it's a solid. So that's my K1. I'm going to multiply it by my K2, concentration of that. Ag NH32. So the concentration of that guy, that's my product, over these concentrations. So silver and the ammonia squared. Alright, so that's my K1, that's my K2, and I'm telling you that this times this will be equal to the K of this overall. Let's go ahead and just write what the K would be for this for the overall reaction, and then we'll compare and see if this side really is equal to that side. So this is going to be concentration of chloride times concentration of that. All divided by the concentration of ammonia squared. Okay, so let's look on this side, and I get to cancel out concentration of silver. That shows up twice, and then this times this is that, and this guy is right there. So hey, K1 times K2 gives you the K overall for the steps.